Welcome back to Fundamentals of DC Circuits. In this video, we're going to discuss parallel circuits and Kirchhoff's current law. The learning objectives for this video are that you will be able to identify a parallel circuit, be able to determine the total resistance, total voltage, and power in a parallel circuit, be able to apply Ohm's law and Kirchhoff's current law to a parallel circuit, and finally, to be able to use a parallel circuit as a current divider. First, let's begin with our definition of what a parallel circuit is. A parallel circuit has more than one branch or more than one path for current to flow through. On the screen, you'll see several examples of what a parallel circuit might look like. Keep in mind that we are not going to base our definition of what a parallel circuit is on the orientation of the resistors, meaning the way in which they are drawn. We're only going to base our definition of a parallel circuit on the direction of current flow and the fact that current has to have more than one branch to flow through. So in the first circuit here, current will leave the voltage source, and at this node, current will split. Some will go this way, and some will go this way. Once the current travels through each of these two branches, it will recombine right here. Because the current splits at this node, the current takes two different paths and then recombines, we call this a parallel circuit. That's the only way we're going to define what a parallel circuit is. It is not based on the fact that these two resistors appear to lie in a parallel orientation. Again, if you go back to geometry and you think about parallel lines, yes, these two lines appear to be parallel, but that's a geometric concept, and that doesn't apply to our definition of what a parallel circuit is in electronics. So again, there's only one definition of a parallel circuit, and it must be that there is more than one branch or more than one path for current to flow through. Here's another example which shows the total current. Again, it leaves the source, it splits into two branch currents, and then recombines. Here's a third example where we have multiple paths, more than two paths. The total current will leave the voltage source here, and then it'll split at this node. Some will go this way, and some will go that way. It'll split again. Some will go this way, and some will go that way. It'll split again. Some will go this way, and some will go that way. Notice that all of the current recombines down here at point B. So the total current that ends up going back into the voltage source is the same amount of current you started out with. So with a parallel circuit, the current will split, take two or more paths, and then recombine, giving you the total that you began with. So to determine if resistors are in parallel, look for more than one current path, or we call that a branch, between two separate points. Keep in mind that the voltage between those 2 points also appears across each of the branches. Resistors in parallel will always have the same voltage. So these are other examples of parallel resistors. And now we can see that we have different orientations. For example, we have a resistor here and a resistor here. But follow the path of current and you'll see that it splits at the node at the top. Some current goes down, some current goes around, and then it recombines right here. So this is a parallel circuit. With image B, we can easily see that the current splits at this node right here. Some takes the path to the left, some will take the path to the right, and then it'll recombine right here. Same thing for picture C and picture D. Now take a look at picture E. This is the picture that will not intuitively look like a parallel circuit. So this is a great example of what I mean when I say don't look at how the resistors are drawn and determine if something is in series or in parallel. Follow the path of current. So with this example here, current will begin to flow here. Current will split here. Some will go up and around this way. Some will go down this way. And then it'll all recombine right here. Therefore, this is another example of a parallel circuit. Always follow the direction of current flow, nothing else. A defining characteristic of a parallel circuit is that resistors in parallel have the same voltage across each of them. So in these two images here, these are all resistors that are in parallel. If a resistor is in parallel with another resistor, they both have to have the same voltage. This may or may not be equal to the source voltage. It depends on the orientation of your circuit. In this example, these three resistors are all in parallel with the voltage source. So they're all going to have the same voltage as the voltage source. But you can have another circuit where all three of these are in parallel, but they're not in parallel with the voltage source. So we don't know what the resistor voltage is, we just know that all three of them have the same amount. If you take a look at the lecture notes, this is the first picture that you have on your notes. And the question is to determine the voltage across each resistor in the circuit below. If you look carefully at this circuit, you can see a voltage source right here of 25 volts. The current has to flow through here, and then it's going to split. Here's one path, here's another path. That path will split here and here. That path will split here and here, and then this path will split here and split here. But if you notice, with all of these paths, they all recombine along the bottom. Every single path recombines to this point along the bottom. Therefore, all of these paths represent parallel paths. So all of these resistors are in parallel with each other, and they're all in parallel with the 25 volt source. They all have the same voltage because they're all in parallel, and in this case they all are going to have 25 volts across for each resistor. Next, we're going to move on to a new law. In the last video we discussed Kirchhoff's voltage law. We also have Kirchhoff's current law. And Kirchhoff's current law states that the sum of the currents into a node, the total current into a node, is equal to the sum of the currents out of that node, or the total current coming out of that node. Keep in mind, a node is any point or junction where two or more components are connected. A node will always be represented with a very visible black circle. If you don't see a very visible black circle, it's not a node. So Kirchhoff's current law states that the current going into a node, for example, this current goes in, we see that based on the arrow, that current going in has to equal the current coming out. And there are three currents coming out. So if we add up I1, I2, and I3, it must be equal to I total. The current going in must equal the current coming out. Same thing with node B. The current going into node B is I1, I2, and I3. If I add all those together, that has to equal the total current coming out of node B. That's what Kirchhoff's current law states. So our first example of Kirchhoff's current law is below. We're going to determine the current. We're going to determine current I2 through resistor 2 in the circuit below. So let's take a minute and analyze what we've been given. We have a circuit with a voltage source. We don't know how much voltage has been applied. We do know the total current going into this node. That's a node right there. From this node, we have three branches, 1, 2, and 3. All three of these branches recombine right here. Therefore, I can say that all three of these resistors are in parallel. They all are going to have the same voltage. In this case, these three resistors are all in parallel with the voltage source. So if I knew the value of the voltage source, I would also know the value of the voltage for R1, R2, and R3. However, that's not the question right now. Right now, we're going to determine the current through R2. And to do that, we're going to use Kirchhoff's current law, which I will now abbreviate with the term KCL. So we have KVL and KCL. So here's what we're going to do. We're going to set up an equation for this node right here. And we're going to represent the currents going in on the left and the currents coming out on the right. There's only one current going in, which is IT, and there are three currents coming out, I1, I2, and I3. If I add all three of these up, it has to be equal to the total current going into the node. Fill in what you know. We know that IT is 100 milliamps, I1 is 30 milliamps, and I3 is 20 milliamps, leaving us an equation we can solve to find I2. So I2 has to be 50 milliamps. Our next example has a circuit with 3 parallel resistors, R1, R2, and R3, and we have 5 ammeters. Remember, an ammeter is just a measurement tool. It's just a tool to measure the flow of current at a certain point. So these ammeters are giving us some measurements. For example, ammeter 1 is saying that there's 5 milliamps of current flowing into node X. So what we're going to do is find the missing currents for ammeter 3. There's no current listed there. And ammeter 5. There's no current listed there. So we're going to use KCL to do this. And we're going to start by analyzing just node X. If you look at node X, first look at what's going into the node. There's only one current going in, and that's 5 milliamps. Then look at what's coming out. The current through R1 and the current through ammeter 3. So set up an equation using KCL. Current going in is 5 milliamps. The current coming out is 1.5 milliamps plus this unknown value here. So I can easily solve this to get A3. So now I know that the current coming out of node X in this direction is 3.5 milliamps. Now if we go over to node Y, we're going to look at what's going into node Y. Notice what's coming out of X is now going in to Y. So we know that 3.5 milliamps comes in, and then that current splits. 1 milliamp goes this way, and the rest has to go through A5. So if I set up an equation to explain that, here's what it will look like. 3.5 milliamps goes into node Y, 1 milliamp comes out, and the remainder has to come out and go through ammeter 5. So then I can solve that to get A5, which is 2.5 milliamps. This is an example of an application of KCL. If you have current sources that are in parallel, the total current produced by those current sources is equal to the algebraic sum of the individual sources. Again, we have this word algebraic sum. That simply means whenever we write a sum of individual currents, we have to include a magnitude and a direction. So current can flow up, down, left, or right. And we have to consider how much current is flowing in each of those directions whenever we write an algebraic sum. For example, in picture A, I have 1, 2, 3 current sources. Each current source is flowing up. So I have 1 amp flowing up, 2 amps flowing up, and another 2 amps flowing up. All of that will combine to give me a total of 5 amps. But let's say that I have the same circuit, but now this current is flowing down. Well, now I'm going to have 1 amp of current flowing down, 2 amps flowing up, 2 amps flowing up. So if I combine the currents that are flowing up, 2 plus 2 would be 4 amps. And then I have to subtract the current that's flowing down because it's in the opposite direction. So that gives me a total of 3 amps that is flowing right here. So anytime that we write a sum of currents, we're always going to have to do it algebraically and consider the direction of the current as well as its magnitude. A general rule of thumb is any current that's going up or to the right, we'll consider that a positive current. Anything that's going down or to the left, we'll consider that a negative current. That way, when you do your algebraic sum, you'll be able to reflect the direction of the current flow. When resistors are connected in parallel, the total resistance can be found by using the following formula. Your RT is going to be 1 over R1 plus 1 over R2 plus 1 over R3, etc. You're going to turn each resistance into a fraction or take its reciprocal, add them all up, and then take the reciprocal of that sum. And you can do this for any number of resistors wired in parallel. So our next example is to observe Ohm's law for a parallel circuit. and this is on page 2 of the notes. For the circuit below, we're going to calculate the total resistance, find the total current produced by the battery, that's the voltage source, and calculate the current through each resistor. So we're going to begin by calculating total resistance. Notice that this is a parallel circuit, so you cannot just add these two resistor values together. You're going to have to use the formula for resistors in parallel. Here's what that will look like. 1 over the 100 kiloohms plus 1 over the 56 kiloohms to the -1 power, or take the reciprocal of that. Make sure that when you type this in your calculator that you reflect that this is a kiloohms for the unit. Make sure that the unit you get out is also kiloohms. You will want to practice that and make sure that you can type in these values correctly in your calculator and get the same answers you see on the screen. So there's our total resistance. Now that we have the total resistance, we can use Ohm's law to find the total current. Total current has to be the source voltage divided by that total resistance value we just found. The source voltage is 100 volts, so you're going to take 100 volts and divide by 35.9 kiloohms to get your total current flowing in the circuit. So keep in mind that total current is what begins to flow from the voltage source. It's then going to split into two paths. So our next goal is to figure out how much goes on each path. So in order to do that, we're going to remember that resistors in parallel have the same voltage. So R1 and R2 have the same voltage. In this case, R1 and R2 are also in parallel with the source. In general, I can say that because there are no other resistors along this path. If there were another resistor right here, I could no longer say that R1 has a voltage of 100 volts because this resistor is going to have a voltage drop as well. So when we're determining resistors in parallel and what the voltage might be, you can only say that these resistors have a voltage that's equal to the source if they're truly in parallel with the source, meaning there's no other resistance along this path. So since we know the voltage for R1, we can find the current through R1 by using Ohm's law. The voltage for R1 is the same as the source, 100 volts. Divide by the value of R1, and you'll get the current through R1, which turns out to be 1 milliamp. Keep in mind that the direction of this current has to be down. IT goes into this node, so the current through R1 and R2 has to be down and to the right. We can use Ohm's law to find the value of the current for R2. Same formula, but now we're just going to plug in R2 on the bottom. And now we get the current for R2 flowing to the right. It's going to be important to always know the direction of your current as well as its magnitude. Now that we're done, don't forget you can use KCL to check your work. The total amount of current going into the node was 2.79 milliamps, and we can see that the total current coming out, if I add IR1 and IR2, is also 2.79 milliamps. So as we learn these tools, don't forget to use them to check your work and make sure that you have applied all of the laws and theorems correctly. For the next example, using Ohm's law and parallel circuits, we're going to determine the total resistance of the circuit below. We're going to determine the value of the voltage source, Vs, and we're going to determine the current through each branch. Let's begin with the total resistance. This is the parallel circuit. All three of those resistors are in parallel, so we're going to use that formula to figure out the value of the resistance. Keep in mind, whenever you combine resistors in parallel, the value that you get out of this equation should be smaller than your smallest resistance. If it's not, you know that something is wrong. There's our total resistance. Now I can use Ohm's law to find the total voltage. The total voltage for that source has to be the total current times the total resistance. V equals I times R. We know the total current is 10 milliamps. Multiply by your 136.4 ohms to get the value of the source. In this case, the voltage source is 1.36 volts. Now that we know the value of the voltage source, we also know the value of the voltage for R1, R2, and R3. All three of these are in parallel with each other. They're also in parallel with the source. Again, if there was another resistor right here, or another resistor right here, or another resistor right here, we would no longer be able to say that all of these are in parallel with each other and the source. So keep in mind, you have to look out for other resistors along the path of current flow before you can say that. In this case, I know the source voltage is equal to the voltage for R1, R2, and R3. So I can use Ohm's law to find the current through each resistor. Here's the current through R1. And there's the direction of R1. It must be flowing down because the 10 milliamps flows in this way. Here's the current for R2. It must also be flowing down in this direction. Here's the current for R3, also flowing down. Don't forget, use KCL to check your work. The current through R1, R2, and R3 should all add up to give you the total current you started out with, which is 10 milliamps. Another tool that we will use with parallel circuits is something called a current divider. In the previous video, we discussed a voltage divider. The voltage divider is used when you have resistors in series. You can calculate how the voltage will divide among them. With resistors in parallel, they have the exact same voltage. There is no voltage divider with a parallel circuit, but we do have current that splits or divides among your parallel resistors. So whenever we have a parallel circuit, it also acts as a current divider. The current, which we'll call Ix, through any branch equals the total parallel resistance, RT, divided by the value of the resistance for Rx. So this is very, very similar to the voltage divider formula, but notice that the fraction has been flipped. The total resistance goes on the top. The resistor that you're trying to find the current for goes on the bottom. With a voltage divider, that would be flipped. So you will have to keep in mind which formula you're using and what goes on the top and what goes on the bottom. Notice that we take this ratio and simply multiply by the total current. This is the total current going into a node. It may not necessarily be the total current in your circuit. It's the total current that's being split between these two things. This is how we use a current divider, and this is the general current divider formula. So we're going to use a current divider to determine the current through each resistor in the circuit below. To use a current divider, we must know the total resistance of all the parallel branches along the path that is being split. So this 10 milliamps is being split and it's going three ways. So we have three paths. When we're using a current divider, we must find the total resistance of those three paths. Now keep in mind, you don't necessarily have to find the total resistance for the entire circuit. What you need is the total resistance for the paths when the current splits. So if I had another resistor down here and another resistor over here, I wouldn't need to include those in my total resistance. I just need to know the total resistance along the paths where current splits. So there's my total resistance. Now I'm going to use the current divider formula to find the current through each resistor. Starting with R1, here's the formula. You're going to have your total resistance divided by R1 times the total current that goes into the node. This is the node where current begins to split. So the total current going into the node is what you multiply by. In this case, we're going to take our RT, which is 110.54 ohms, divide by R1, which is 680 ohms, and then multiply by the total current going into the node before it's split. We'll repeat this for R2 and R3. This is how we use a current divider to find the current that goes through a particular branch. Remember that all resistors in parallel have the same voltage, so if you use Ohm's law to find the voltage for R1, R2, and R3, using the currents that we just found for each resistor, you'll see that they all have the same voltage. Lastly, don't forget to use KCL to check your work. The current through R1, R2, and R3 should all add up to the 10 milliamps you started with before it split. Here's another example of a current divider. In this example, there is no voltage source shown, but we know that the current going into this node is 100 milliamps. Some will split and go this way, some will split and go this way. We're going to figure out how much current took each path. To begin, you need to know the total resistance of your two paths. Then you're going to set up the general voltage divider, general current divider formula. For IR1, that's going to be the total resistance over R1 multiplied by the total current going into the node. Repeat this process for R2 by simply changing the denominator from R1 to R2. And don't forget to use KCL to check your work. When it comes to power in parallel circuits, the formulas that you were shown for series circuits still apply here in a parallel circuit. We're still going to calculate power the exact same way. The power for an individual resistor called Rx would be the current through that resistor times the value of that resistor, or the voltage across that resistor times the current through the resistor, or the voltage across that resistor squared divided by that resistor's value. Any one of these formulas will work to find the power for a specific resistor. We also have the same formulas for total power in the circuit, and again, this relies on knowing the total resistance of the circuit, the total current in the circuit, as well as the source voltage applied to the circuit. So the next problem that we'll do is an example of how we calculate power in a parallel circuit. For the circuit below, we're going to determine the total resistance of the circuit, the total power in the circuit, and determine the value of the applied source voltage. So to begin, the total resistance has to be, these three resistors are in parallel, so we're going to use the parallel resistance formula. 1 over 68 ohms plus 1 over 33 ohms plus 1 over 22 ohms. Take all of that and invert it, and you'll get 11.05 ohms. We can then use this formula. Power is I squared times R. We know the total current and we know the total resistance, so we're going to plug those values in to get the total power in the circuit, 442 milliwatts. Since we know that the total power is also equal to the source voltage times the total current, we can rearrange this to say that the source voltage has to be the total power divided by the total current. Then we can take the total power we just calculated, divide by the total current to figure out what the source voltage has to be. In this case, 2.21 volts. Lastly, we're going to determine the power in each of these resistors. All of these resistors are in parallel. They're all in parallel with the voltage source, and we just discussed that the voltage source has a value of 2.21 volts. That means each one of these resistors also has a voltage of 2.21 volts. So I can figure out the power for each resistor by taking that value of the source voltage, 2.21 volts squared, divided by the value of the resistor R1. I can repeat that for each resistor in the circuit because they're all in parallel. They all have the same voltage, so we can use the same formula 3 times. When you're done, add all of these up, and you'll get something very, very, very close to the total power we previously calculated. This just proves that when you take the individual amounts of power for components in the circuit and add them up, you'll end up with the total power that you calculated using total resistance and total current. And that is the end of this video.